Hello! In this video we're going to be looking at a very interesting phenomenon about multiplication of matrices. It turns out that if you have two matrices, A and B, you can multiply them as follows. The product of A and B will be A times x1 as a first column, and you might be wondering here what is x1, and maybe it shouldn't be x1 at all. Maybe it should be called b1, and the second column will be ab2, and so on, and the last column will be abn. Do I want it to be n? Let me see. Maybe I don't want it to be n. Maybe I want it to be k. What does this all mean? What are we doing here? Well, the thing is that firstly, let us say what dimensions are the matrix, or what are the dimensions of the matrices we're working with, right? So let's say A is an m by n matrix. Okay, what about B? Let's say that B is an n by k matrix. The n here for the B matrix and the n there for the A matrix, of course, should match each other. Otherwise, the matrices, it will not be possible to multiply them, right? Wonderful. Now, what about the B1 up to BK? What are they? Well, they are names of the columns of the matrix B. And we can write it like this. B1 consists of, B consists of the column B1, column B2, and all the way up to column BK. And when B1 up to BK are columns of B, it turns out that A times B can be rewritten like this, where we have the matrix A multiplied by the column B1, and so on and so forth. Moreover, this formula can be expanded further. Let us now introduce a similar decomposition of the matrix A, not in terms of its columns though, but in terms of its rows. How many are there? How many rows does A have? Well, it's an m by n matrix, right? So it's going to have, let's see, m rows, right? So let's call them A1. Oh, but now I don't have to write them like this. Now I need to write them like this. A1 all the way up to AN. No, AM. And here I notice that I ran out of space. So I need a bigger bracket. So let's say the matrix A has rows A1 up to AM. So each of these AIs represent the ith row of the matrix A. In that case, we can further write down the following. A1 times B1 all the way up to A1 times BK. Then in the second row we have A2 times B1 all the way up to A2 times BK. And it goes on until the last row where we have AM times B1 all the way up to AM times BK. Really? Is it really so that A times B is going to be equal to this thing? Well, why are we surprised about that? In fact, we know this already. Look, I'm going to convince you that we know this already. How does matrix multiplication work? when you have two matrices and you multiply them, what are you going to put at a position where the row index is I and the column index is j? The answer is clear. From the way we learn to multiply matrices, what we're going to put there is we're going to take the ith row, jth column, so this is the ith row, that's the jth column in the second matrix, and we're going to entry by entry multiply each of the entries of the ith row and the jth column. Their number, by the way, will match. The number of entries in the ith row will be exactly n, and the number of entries in the jth column will also be n, because A was m by n matrix and B was n by k matrix. And so we're going to multiply them term by term and then add these products. But that is nothing other than taking this row matrix and multiplying by that column matrix. And that's exactly what we've got here. You see, for example, in the first entry here, where the I is 1 and the j is 1, we have the first row A1 of the A matrix multiplied by the first column of the B matrix, which is B1. And in the last entry here, we have the mth row of A times the kth row, kth column, my apologies, times kth column of the B matrix. So the fact that A times B is equal to this matrix is something that we actually know quite well. It's just that we never thought of it this way. We know it quite well by the rule that we learn to multiply matrices. So now coming back to this first equality, then that shouldn't be surprising at all, because if I look at the first column of this, I see I have there A1 times B1, A2 times B2, and so on, and where the A's are the rows of A, and B1, remember, it's a column matrix. So what would be the answer to a matrix product if the right-hand side matrix is a column matrix? By similar rule as for the matrix multiplication in the general case, we would have that the first entry here is the first row of A multiplied by the first and unique column of B. So that's A1, B1. And the second entry here should be second row of A multiplied by the first column of B, just like here. Each entry was, at ij position, was ith row of A multiplied by jth column of B. And so by the same principle that we explained here, A times B1 is going to be a column consisting of A1, B1, A2, B2, B1, and so on up to AM, B1. And so, by grouping these together, we get the other formula, where we say that A times B is given by a matrix whose columns are A times B1, A times B2, and so on up to A times BK, where the B1 up to BK are the columns of the matrix B. Perhaps it is worthwhile to demonstrate this on a concrete example. So let us now take a concrete matrix A equals 1, 2, 3, 0, 1, 2, 3, 0, 1. And let's take B equals for some reason I chose a 3 by 3 matrix. Maybe that's not a very good idea, because the rule doesn't only apply to square matrices. So let me extend the matrix with one more row. So let's add another row here which will have 0, 1, 2. And let B be the matrix. So now B needs to have 3 rows because A had 3 columns. So let's have them 0, 1, 0. And let's have 2 columns for B, 0, 1, 0 and 1, 0, 1. Let's multiply them in the usual way. We multiply matrices, and then we're going to multiply them in the way we suggested previously, and then we'll compare the result. So the usual way of multiplying them is going to give us what? So what do we put here in this entry? We're going to go this way and in A and downwards in B, right? Multiply term by term and then add. Okay? So that's going to be 1 times 0, which is 0, plus 2 times 1, which is 2, plus 0 times 3, which is 0. So it's going to give us 2. Then, for the second entry in the first column, the same, but now we work with the second row of A. Then it will be 0 times 0, 1 times 1 is 1, and that's also 0, so it's going to be 1. So you see, because of the zeros here at the 1 in the middle, we're always going to be picking out just the middle term there. So the next entries are going to be 0 and 1. So we've managed to fill the first column. But look at this. How did we fill the first column? We basically multiplied the matrix A by the first column of B. And that's what exactly the rule says, the formula here, right? That the first column of the product is going to be the matrix A times the first column of B. And now I want to fill the second column of the AB matrix, and it is only going to have 2 columns, right? Because B had 2 columns. So the AB will have as many rows as A has and as many columns as B has. And so to get the second column, what we need to do is to cross over this way and here this way. Okay? So 1 times 1 is 1, then 0 times 2 is 0, and then 3 times 1. So according to this column, all we have to do is to take the first and the last and add them, right? So it's going to be 1 plus 4. Then it's going to be 2, 4, and 2. But what is the procedure we followed here? We multiplied each row by the second column, and then we wrote them out as a column here. So we did exactly what this suggests us to do, which is to, in the second column, to have matrix A times the second column of the matrix B. Okay, so we worked out the answer here using the usual way of multiplying matrices, but we did remark that we already here, with this calculation, see the link with the other formula. But let us now explicitly work out the answer that the other formula would give. And namely, let us work out, first of all, let us write out explicitly what B1 and B2 are. So it's going to be 0, 1, 0, and B2 is going to be 1, 0, 1. And let us explicitly work out AB1 and AB2 separately. So what is going to be AB1? AB1 will be the matrix A times that column. So we'll have to go across this way, right? And downwards that way. And you can see now we are really doing the same thing. And because of the middle entry being 1 and the outer being zeros, it will pick out the middle entry. So it's going to be 2, 1, 0, 1. And AB2 is going to be, now this one is going to add the outer terms and disregard the middle term. So it's going to be 4, 2, 4, 2. And of course, AB, as we can see from this specific calculation, is indeed equal to AB1, AB2. Indeed, AB1 matches with the first column of AB, and AB2 matches with the second column of AB. And in exactly the same manner, if you want to, on an example, you can confirm that we've got AB also represented in this way, where we break up the columns further down into rows.